Dear students, in the last class we completed the problems on the limit form of comparison test, and then also we completed the problems on D-Alembert ratio test, right? In the D-Alembert ratio test we have three cases. First case, when L greater than 1, divergent, L less than 1, convergent, and when L is equal to 1, test fails. Whenever L is equal to 1, test fails. Generally we go to limit form of comparison test if x is involved by substituting x is equal to 1. Now in this class we will see, I am going to explain the next concept, which is Cauchy's nth root test. The name itself given that nth root test. That means the given series, if un consisting of nth power of itself as a whole, then only we can use this Cauchy's nth root test. The rule is, let sigma un be a positive series and limit n tends to infinity un to the power 1 by n. 1 by n means power 1 by n means nth root of un is equal to some L, limit value is L. It is a finite value, right? Then the series sigma un is convergent if L less than 1, sigma un is divergent if L greater than 1, test fails when L is equal to 1, right? So first we need to calculate limit n tends to infinity un to the power 1 by n value. If that value is L, L value must be a finite value. If L value is less than 1, convergent. Divergent if L value greater than 1, test fails when L is equal to 1. In that case we have to go to the use another test, that it may be a limit form of comparison test, otherwise any other test, right? Here Cauchy's nth root test. Cauchy's nth root test is applicable, otherwise generally we are applying if un consists of the nth term un consists of nth power of a term itself as a whole. That is, un is equal to some x plus 3 by x plus 2 whole to the power n. Some power n is there, then we apply this Cauchy's nth root test, right? Now we see the problems on this Cauchy's nth root test. Test for convergence of sigma n plus 1 by 2n plus 5 whole to the power n. Term whole to the power n is there, then we apply the Cauchy's nth root test. What is un here? Un is n plus 1 by 2n plus 5 whole to the power n. Now find out limit n tends to infinity un to the power 1 by n. What is un? n plus 1 by 2n plus 5 whole to the power n whole to the power 1 by n. N gets cancelled. Taking common n from both numerator and denominator, 1 plus 1 by n into n by n into 2 plus 5 by n. N cancel. As n tends to infinity, 1 plus 0 by 2 plus 0, 1 by 2. Here the limit value is finite value and which is less than 1, implies by Cauchy's nth root test. Given series is convergent, right? Next one, test for convergence of sigma n equal to 2 to infinity 1 by ln means log base e, log of log n whole power n. Because this un consisting of whole to the power n is there, we apply the Cauchy's nth root test. So what is un here? Un is 1 by ln of n whole to the power n, right? So now consider limit n tends to infinity, un to the power 1 by n. What is un? 1 by ln of n whole to the power n, again power 1 by n. This n cancel with this n. ln of n. As n tends to infinity, ln of n also tends to infinity. Ln of again infinity. So 1 by infinity it becomes 0. It is the limit value. 0 is a finite value which is less than 1. Implies given series is convergent. Right? As n tends to infinity, log infinity value is infinity. So the next one, test for convergence of sigma x power 2n by 2 power n with x greater than 0. So what is the nth term? Given that nth term un is equal to x power 2n by 2 to the power n. Right? It is like x square by 2 whole to the power n form. Because un consisting of nth power as its whole, so we apply Cauchy's nth root test. Consider limit n tends to infinity, un to the power 1 by n. Limit n tends to infinity, x square by 2 power n whole to the power 1 by n. As n tends to infinity, these two gets cancelled. The term which does not contain any n, so it is x square by 2 only, which is L value. Right? So here we have different cases. Case 1, when limit value L is equal to x square by 2 less than 1, that is x square value is less than 2. Given series is convergent. X square less than 2, otherwise we can write it as x value less than root 2. Case 2, right? X value is less than root 2. When limit value x square by 2 greater than 1, that is x square value greater than 2, given series is divergent. Now we see case 3, that is the failure case. What is case 3? When limit value L is x square by 2 is equal to 1. When x square is equal to 2, that is x is equal to root 2. Actually it is plus or minus root 2, but here we are applying the Cauchy's nth root test only for the positive series. So test fails. We consider only positive value. So whenever the test fails, we have to substitute the corresponding x value in un value. What is un here? X square by 2 whole power n. So it becomes x square is equal to 2. So 2 by 2 whole power n. It is nothing but 1, right? So 1 can be written as 1 by n to the power 0. Implies sigma un is equal to sigma 1 by n to the power 0. It is in the form of summation 1 by n power p, which is convergent value is 1 by n power 0, which is equal to 1, is divergent for p value less than or equal to 1. What is p value here? P is equal to 0. P is equal to 0. So 1 by n power p, which is divergent when p value less than or equal to 1, convergent when p greater than 1, implies series is divergent when x square is equal to 2. So now we have to write down overall conclusion. Therefore, given series is convergent when it is convergent when x square less than 2. And divergent when x square greater than or equal to 2, right? This is the problem. Well, like that, whenever the case 3 test of failure is there, we have to apply any suitable test and decide whether the series is convergent or divergent. This failure case is occurred in both the ratio test and also as well as Cauchy's nth root test. So the next one, test for convergence of sigma, otherwise summation 1 plus 1 by n whole power 2n by e power n. Both the numerator and denominator is in the form of power n. So we apply Cauchy's nth root test. So here nth term un is equal to 1 plus 1 by n whole to the power 2n by e to the power n. Now consider limit n tends to infinity un to the power 1 by n. Limit n tends to infinity 1 plus 1 by n whole square by e whole to the power n. We can write like this un. Un to the power 1 by n. This n cancel here. Now apply as n tends to infinity. As n tends to infinity, 1 by n tends to 0 whole square by e, which is 1 by e. E value is 2 point something. So 1 by e value is less than 1, implies given series is convergent by Cauchy's nth root test. Right, with this Cauchy's nth root test also completed, one more test is there on positive series, which is the integral test. After completing that, then we are moving to the alternating series. Thank you.
Hi students, in the previous classes we have seen how to find out the nature of the series using the p-test, that means harmonic series test, then geometric series, and then limit comparison test. After that, already we discussed the problems on Cauchy's nth root test and also D'Alembert's ratio test. Now in this class I am going to explain the topic of integral test. Otherwise, the other name of integral test is Cauchy's integral test, right? So, what is Cauchy's integral test? Summation un is equal to u1 plus u2 plus u3 and so on plus un and so on. Here, it is a positive series. So, series with positive terms and non-increasing terms. The meaning of non-increasing terms is u1 greater than or equal to u2 greater than or equal to and so on. That is, in general we can say that the nth term un is greater than or equal to un plus 1. The terms of a sequence are gradually decreasing, right? So, in the two conditions are essential to apply the integral test. The first one is the series must be positive series, and the second condition is the sequence terms un must be decreasing as n tends to infinity, right? Let f of x be continuous non-increasing function such that un is equal to f of n. So how to consider f of n means by using the nth term of the sequence un is equal to f of n. Then the improper integration 1 to infinity f of x dx is finite. Then the series is convergent. So here we are finding the nature of the series using the integral. So we call it as integral test. To say that sigma n equal to 1 to infinity un is convergent if the improper integral integration 1 to infinity f of x dx is finite. If the integration value is infinity, then the series is not convergent. In other words, we can say that the series is divergent, right? Now we will see the problems. The first one, determine the nature of the series 1 plus 1 by 3 plus 1 by 5 and so on plus 1 by 2n minus 1 and so on. Right? You know how to write down the generalized, otherwise nth term of the series. So nth term un is equal to, if you observe the first term is 1, second term is 1 by 3. So nth term is 1 by 2n minus 1. Right? 1 by 2n minus 1. Now here how to take f of x means we have to write f of n is equal to un. So take f of n is equal to un is equal to 1 by 2n minus 1. Then consider the improper integral. Consider I is equal to integration 1 to infinity f of x dx. So what is f of x? 1 by 2x minus 1 dx. Right? You know how to integrate it. 1 by 2x minus 1 multiply by 2 and divide by 2. Now it is of the form integration f dash x by f of x dx is equal to log mod f of x. Right? So which is equal to half into log mod, denominator term is 2x minus 1 within the limits 1 to infinity. Right? So now substitute the upper limit half into, put x is equal to infinity. So 2 into infinity, infinity minus 1, infinity, log of infinity is infinity. Then put x is equal to 1, log of 2 into 1, 2 minus 1 value is 1, log 1 value is 0. So infinity by 2 is also infinity. If the integral value is not finite, because we are getting infinity, so it is not finite. Because it is not finite, therefore given series 1 plus 1 by 3 plus 1 by 5 and so on plus 1 by 2n minus 1 and so on, which can be written as sigma n is equal to 1 to infinity 1 by 2n minus 1 is not convergent by using integral test. So when the integral test is applicable if the integration is easy, right? Otherwise, if integration is difficult, we cannot apply the integral test. One more condition is here, because the summation n starts with 1, so we are taking the lower limit of integration as 1. Suppose if n starts with 2, then the lower limit of integration we will take it as 2, right? And now we will see the next sum. Test for the convergence of the series sin pi plus 1 by 4 sin pi by 2 plus 1 by 9 sin pi by 3 and so on. Find its nature. Nature of the series means it may be convergent or divergent but not oscillatory, because it is a positive series. Only we have two possibilities. One is it may convergent, second one is it may divergent but not oscillatory, right? So first we have to express this in terms of generalized form. What is the first term? Sin pi. So first term is sin pi. Second term is 1 by 4. 4 can be written as sin 2 square sin pi by 2. Now third term is 1 by 9 means 3 square sin of pi by 3. Now by observing this pattern, write the nth term. and so on. Nth term can be written as 1 by n square sine of pi by n, right? So like that we are writing the generalized form, otherwise nth term. Then given series can be written as summation n equal to 1 to infinity 1 by n square sine of pi by n, right? 1 by n square sine of pi by n. Now by using the integral test, we have to decide the nature of the series. To decide that one, we have to choose f of n. So how can we take f of n or f of x? F of n is equal to nth term un. Un is the term after this sigma. What is the term? 1 by n square sine of pi by n. In this sigma, n starts with 1 to infinity, so that in our improper integral, right, consider integration I is equal to lower limit of this sigma is 1 to infinity f of x dx. Now evaluate this integral. If this integral value is finite value, then the given series is convergent. If the integral value tends to infinity, then the given series is divergent, otherwise not convergent, right? So what is f of x? 1 by x square sine of pi by x dx. To evaluate this integral, take pi by x is equal to some t. Doing differentiation on both sides, minus pi by x square dx is equal to dt. So dx by x square is equal to minus pi into dt, right? So now we have to find out the new limits. Previous limits are when x is equal to 1. When x equal to 1, put x is equal to 1, we will get t new limit is pi. When x is equal to upper limit infinity, pi by infinity is 0. So what is the t value? 0. Now our integral I is equal to integration. When x is 1, new limit becomes pi. When x is infinity, new limit is 0. So sine of pi by x is sine t. Dx by x square is minus pi into dt. So to remove this minus, otherwise make it as plus, integration a to b, we can write it as b to a. So it becomes 0 to pi sine t dt, because pi is constant right before. So what is integration sign? It is minus cos t, 0 to pi. Then substitute the limits, which is pi into cos pi value is minus 1. Cos 0 value is 1. So what is the value? Here already negative sign is there. If you have any confusion, write before, then substitute it. Cos pi value minus 1, cos 0 value 1. So it is 2 into pi. Because 2 pi value is finite value, by using this integral test, if integration 1 to infinity f of x dx is finite, then the series is convergent. If it is infinity, then the series is divergent, right? So we can write down, because it is finite, thus the given series is convergent. By which test? By integral test. Right? Like that we apply the problems on integral test to find out the nature of the series. Right? What is the demerit of this test means if the integrand is some complicated function, in that case we cannot find out its integration. Therefore, integral limit test is applicable only if the integrand is suitable to integrate it. Right? Right, next sum. Prove that summation n equal to 2 to infinity 1 by n into ln of n divergence. Right? Here what is un? Nth term un is equal to 1 by n into ln of n. Right? So to apply the integral test, we have to take f of n as un. So take f of n is equal to un, which is 1 by n into ln of n. Ln of n means log base e. Now consider integral I is equal to integration. But to write the limits of the integration, we have to careful about this summation sigma, where this sigma n starts with 2. So integration lower limit is 2 to upper limit is infinity f of x dx, which is integration 2 to infinity. What is f of x? 1 by x into ln of x dx. So take ln of x is equal to t, otherwise which is same as log x is equal to t. So its derivative is 1 by x dx is equal to dt. What about the previous limits? The limits are 2 to infinity, right? So when x is equal to 2, now t becomes ln of 2. When x is equal to infinity, t becomes ln of infinity is infinity. So it becomes integration 2 to infinity, not 2, it is ln of 2. So 1 by x dx is dt by t. If you observe here, this 1 by x dx value is dt. So integration 1 by t is ln of t. Sometimes we can also write it as a log of t, both are same. So ln of 2 to infinity. Substitute the upper limit infinity, right? So ln of infinity is infinity minus, put the lower limit ln of 2. Because ln of 2 is a finite value, again ln of finite value is finite. Infinity minus finite value, it always tends to infinity. Implies integral I is not finite. If it is finite, the corresponding series is convergent. But it is not finite, therefore the corresponding series by integral test given series sigma n is equal to 2 to infinity 1 by n into ln of n is not convergent. Or it is divergent. Right? It is divergent. This is about integral test. With this, the tests on positive series are completed. We discussed the comparison test limit form, p-test, then geometric series, D'Alembert's ratio test, then Cauchy's nth root test. This is the Cauchy's integral test. These are the several tests to apply to find out the nature of the given series. In the next session, we will see the alternating series. What is meant by alternating series? Till now, we are discussed only about the positive series. All these tests are applicable only on positive series. Whether it may be a geometric series or p-test, otherwise a Cauchy's nth root test, otherwise integral test, or D'Alembert's ratio test. All these are applicable only on positive series. Suppose if the series is an alternating series, means that some of the terms are positive and some of the terms are negative, then we have a separate test. We call it as a Lebanese test. In the next class or in the next session, we will see how to find out the nature of the alternating series, right?